If I am sliding to a stop in a game of baseball, I'm sliding into home base. So here's my body sliding along the dusty dirt, and I'm trying to get to home base there. Okay, so I'm sliding home base. Well, I jump and I slide and I slow down. And so looking at all the forces acting, well, there's a force of gravity pulling down and a normal force counteracting and pushing up, and I'm not accelerating up and down, which means I know those two forces are equal. But horizontally, the important motion here is that I'm slowing. Hopefully I can still reach that base before I get tagged by the ball. Okay, but I'm sliding this way and I'm slowing down, which means there must be a force acting in the opposite direction. I know my acceleration is that way, my velocity is this way, and I'm slowing, so my acceleration is opposite. And therefore I know there must be a net force in the x direction. Okay, and what is that from? Well, the normal force can only act vertically, okay, but there is a frictional force, and so it's clear that friction is what's slowing me down. And so I can relate that. Now here's a couple trickier problems. Okay, what if I have a box sitting on a floor, it's on carpet in fact, and I'm standing there pushing on this box. Okay, so I'm pushing with all my might, but the box is not going anywhere. Right? Well, that tells me F net is 0, both up and down and side to side, because it's not going anywhere. So if I think about the forces acting on this box, I'd say, well, in the vertical there's the normal force, gravitational force, like I saw before, and since I don't see anything else that could be applying a vertical force, those two must be equal and opposite because there's no acceleration vertically. Horizontally, it's not accelerating either. And so I look and I see there's the box isn't going anywhere, so maybe initially I don't want to say there's friction, but I'm pushing on that box. So there's a force from this push that is to the right, but it's not going anywhere, and therefore it's not accelerating. So there must be another force. The only way that can engage is through this frictional force. Okay, so the frictional force is there. And we generally have a rule that says friction opposes motion, which is true. Friction opposes motion. Here it's obvious. My motion was to the right, and friction was to the left. The frictional force opposed the motion. But this box is not moving. And so what is the frictional force? It's opposing what motion? Here's what I like to say that's consistent with this picture up here. So I do like to say friction opposes motion. What I'd say here for this object that's not moving, I'd say friction opposes the motion that would happen had there been no friction. Okay, so let's digest that and say, okay, let's suppose instead of on carpet, this is on slick ice, okay, or it's on a cart that's got really well-oiled bearings in the wheels, something like that. So basically zero friction. Okay, if I push on it, it's going to go this way. It's going to go to the right. So that would be the direction. My pen's dying here. Oh boy. I'm going to change colors. Okay. So my motion would be to the right there. Okay. And so then I could say, oh, that's the motion that would have happened, okay, in the absence of friction. But since I have friction, that frictional force must oppose that motion. And so I'm saying that the frictional force is to the left. Now let's take a look at a free body diagram and make sure that that is accurate, especially confirming that our net force must be 0. So if I put a dot to represent my box here, and vertically I have a normal force, okay, and down I have a force of gravity, okay, and I have this push force that is this way. We put FP for push force, and I've indicated that my frictional force must be the other way. I can see that here as well because I have to have a leftward force so that my net force in the x direction is 0. And so I also know that it's just as big as that push force since it's not moving. Okay, so the frictional force opposes motion, as we see in this case, or it opposes the motion that would have happened had there been no friction. Now let me step this up one little bit. what if I was pushing this box and it was moving? It was moving at constant speed. How would this be different? And I hope you caught that the answer is it wouldn't be different at all. Okay, it's moving now, and so my frictional force is opposing that real motion, but if it's moving at constant speed, this is still true. F net is still 0. And so my forward push force must be equal to the frictional force. It's just I had to do something earlier on to get it moving. Okay, but once I got it moving, if I'm pushing it at constant speed, then the net force is still 0, and the force free body diagram looks the same. Okay, now with that established, let's try and apply that to a problem I like. Suppose I have a turn in the road. Okay, there's a turn in the road, and here's my car. There's the dotted lines. I guess I'm driving right in the middle of the dotted lines, so forgive my poor driving here. All right, but this car is moving around this curve, so it's going around the curve this way. Okay, and so initially it's going this direction, and then later on it'll be going this direction. And so if this is v initial, and that's v final, then my acceleration is the vector difference of those two. My acceleration must be something like this. Okay, this must be my acceleration vector, because it was initially going this way, and now it's going this way. So it both changed direction, so I've got a component that was this way, and it's no longer going up, so there must have been something to slow it down in the upward direction as well. Okay, so it turned here. Alright, now if that's the direction of my acceleration, well, the net force better be in that direction too. Okay, the net force better be in that direction. So if that's the case, then I need to think, what are the forces available to do that? Well, this is kind of a three-dimensional problem in a sense, that I've got a normal force holding up the road, holding it up, so that's going up, out at you. Gravitational force is going down, away from you. We'll kind of ignore those right now, but what we will focus on is the horizontal forces on the road. So this car is turning, and its acceleration must be inward, and so its net force must be inward. What did that? Okay, let's ask this question. If there were no friction on this road, let's say there's an ice slick right there, or a puddle of oil, what would happen to this car? So there's a big ice slick right there. What would happen to this car? This car would enter that ice slick and not be able to turn. It would go right on through, straight on through. So that's what would happen if there were no friction, which means friction is what makes it turn. We kind of want to say things like the turning is because of the force of the wheels. The wheels turned and therefore it turned. But you have to remember that the wheels are part of the car, and so they can't act on itself. Something about forces, when we think about Newton's second law, is we have to think about all the external forces acting on the particle. So the wheels are part of it. And so yes, we do turn our wheels to turn, but if there was an ice slick here, that would do nothing. So the end result is that friction is the force, because we see without it, I would have gone straight. I would not have accelerated, and therefore my net force would have been 0 in that direction. Okay, so friction is what caused this to turn. And we don't often think about that. Friction actually helped this turn this way, because in the absence of friction, it would have gone that way. Okay, one last example is a car driving along a road. We're going to assume this car is a front-wheel drive car. That means the power is to the front wheels. The engine turns the front wheels. The back wheels just roll along the surface by virtue of being pulled forward. So I'm going to ask, what is the direction of the frictional force on the front wheels relative to the back wheels? Okay. So we have to think carefully. There is a friction, like if I got this car going at a constant speed and it popped into neutral, so there's no power to the wheels, it would eventually slow to a stop, which means there's got to be a backward force of friction that kept it slowing down. And that backward force is on both wheels. Okay, it's called rolling friction, and there is a rolling friction that resists the motion that does occur. Okay, And so that's just like a normal motion, like me sliding into home base. But when there is power to the drive wheels, okay, in this case the front wheels, then those wheels are pushing back on the road, and if there were no friction on that part, those wheels just spin. But because there is friction, that frictional force pushes the wheel forward. The wheel tries to push the road back, but the road actually pushes the wheel forward. And so it's that driving, that we call that a propulsion force, but now we can isolate it and understand it is due to friction. So there's a frictional force here that is due to the drive. I'm going to call it F sub P, okay, but it's actually a static friction, okay, to be clear. It's a static friction because we're hoping that the wheel doesn't spin out. So the actual contact point between the wheel and the road doesn't move relative to each other. And so that's a static friction, but it's where we get propulsion from, is as we were pushing back on that. So all of this is a thorough overview of how friction works. And the main idea to think about it is to ask that question, what would happen if there were no friction in the system? And that helps you to indicate the proper direction of the frictional forces in each of these cases.